Hello everyone. So in this lecture we are going to start our second chapter. As you can see, making of nanostructures, top-down approach. Okay. So as far as nanomaterials are concerned, now you all are familiar that what is a nanomaterial. Okay. So what is a nanomaterial? A material whose all the dimension or at least one of the dimension should be at the nanoscale. It's called as a nanomaterial, right? So if you know what is a nanomaterial, you are also familiar with different types of nanomaterial, right? That is a three-dimensional nanomaterial, two-dimensional nanomaterial, one-dimensional nanomaterial, and zero-dimensional nanomaterial. So you are aware about the nanomaterials and different types of nanomaterials, but now what you are going to learn is how to synthesize these nanomaterials, how to prepare these nanomaterials. Okay, what are the techniques, okay, which we can use to make these nanomaterials? So that we are going to see in two chapters, in the second chapter and the next third chapter. And we have made these two different chapters because we have classified the synthesis techniques based on two broad approaches. Okay, one is a top-down approach and second is a bottom-up approach. So these are two broad approaches by which one can synthesize the nanomaterials. Okay, what is top-down approach, what is bottom-up approach, that we will see in this chapter. Okay, so basically in this chapter what we are going to see the synthesis techniques which belongs to top-down approach. Okay, so what are these techniques? Mechanical grinding, it is also called as a ball milling. Okay, this is a technique which comes under top-down approach. Photolithography. Okay, so we will see what is lithography. Okay, what are different types of lithography. Okay, how you can do the lithography, and what is photolithography. Okay, electron beam lithography. This is what we everything what we are going to see in this chapter. And after this we are also going to see some thin film technologies. So thin film is basically 2D, comes under 2D materials, two-dimensional materials. So one of the dimension is at the nanoscale. So it is called as a thin film. So it is a film basically with X and Y will be anything in the scale, in the length, but only thickness is coming under the nanoscale. Okay, so in thin film technologies, basically what we are going to see is a vacuum based technologies which is called as a sputtering. Okay, PLD is a pulsed laser deposition. The long form for PLD is pulsed laser deposition. CVD, the long form for CVD is chemical vapor deposition. Okay, long form for CVD is chemical vapor deposition, and long form for ALD is atomic layer deposition. Long form for ALD is atomic layer deposition. So these are the techniques which we are basically trying to cover in this chapter. Okay, so as far as synthesis is concerned, okay, we what is our motive is to learn how to synthesize these nanomaterials. Okay, so as far as synthesis is concerned, depending upon the way, okay, uh, there are four types of synthesis techniques. The first is a physical technique, second one is a chemical technique, third is the biological way to make the nanomaterials, and the last is a hybrid. Okay, so in the physical way there are two different types. One is a mechanical and second is a vapor. In mechanical, okay, we are using mechanical energy to make the nanomaterials. What is the examples for this mechanical way? Is a high energy ball milling, melt mixing. So here basically we are trying to understand what is high energy ball milling. That is a mechanical way of synthesis of nanomaterial. And in case of vapor, okay, you can see there are different techniques by which we are able to make the nanomaterials. So it is called as a physical vapor deposition because we are under the physical category. Then we call this as a physical vapor deposition. Laser ablation. We use laser to prepare the nanomaterials. And ablate means we bombarding. We are bombard the laser pulses to make the nanomaterials. Sputter deposition, okay, and electric arc. So these are the techniques which are coming under the physical techniques, physical vapor deposition techniques. The second one is a chemical. Okay, in a chemical way, uh, we are able to make the nanomaterials by using colloids, sol gel method, LB films, okay, and inverse micelle. That are these are the techniques which are coming under the chemical way of synthesis of nanomaterials. What are the biological methods? Using biomembranes, DNA, enzymes, and microorganisms. Okay, so these are the biological methods by which one is able to make the nanomaterials. And the hybrid means it is not coming under a particular category. Okay, it is coming. It is a mixture of physical and chemical technique or chemical and biological technique. Okay, so this is a hybrid. Okay, electrochemical. Okay, electrochemical method, chemical vapor deposition. Okay, these are the names of methods. Okay, you have to remember that these are the name of methods by which you are able to prepare the material. Particle arresting in glass or zeolites or polymers is nothing but a kind of a composite, right? Because particles you are adding in glass or zeolites or polymer is a kind of a composite. Micro emulsion, okay, and zeolite. Okay, so these are the ways by which one is able to make the nanomaterials. Now these are the different techniques, okay, but as I said there are two broad approaches to make the nanomaterials, and these two broad approaches are top down and bottom up approach. So in the bottom up approach, okay, what is bottom up approach? So in this approach atoms and molecules are assembled so as to have nanomaterials of required size and shape by controlled deposition or reaction parameter. Okay, so what you have to remember is that in a bottom up approach atoms and molecules they come together to form the nanomaterial. Okay, and I will say that this is a natures, in naturally synthesized materials, most of these materials are synthesized by bottom up approach. Okay, so you have a atoms, they are coming together, molecules, they form molecules, molecules come together and they form some solid material. Okay, so this is a bottom up approach. In the top down approach, okay, reverse is the case. Okay, in the top down approach, reverse is the case. So reverse means what? Atoms and molecules are removed from a bulk material. Okay, so you have a bulk material and you are making it smaller and smaller, okay, so as to obtain the desired nanostructure. Okay, so if you grind something, okay, for example, suppose you want to you have a wheat grains, okay, wheat grains, and then what you do, you go to some milling machine and make it a powder. Okay, you grind it and make a powder of the wheat. Okay, so what this technique is called as a, this is a top down approach. This is a top down approach. Okay, so to understand, for imagination, here is the cartoon, okay, picture, where you can try to understand what is the difference between top down and bottom up approach. So as I said, the top down means you have a bulk material, big bulk material, and what you are doing, you are making a smaller and smaller pieces of that bulk material. Okay, suppose you have a sugar crystals, sugar crystals, and what you are doing, you are grinding it to make the, okay, fine sugar powder. Okay, so this is a top down approach. What is the bottom up approach? In the bottom up approach, the atoms and molecules, they come together, okay, and they started to grow to form the nanomaterials. Okay, so these two are opposite approaches. Okay, from in the top down, you are taking big material, okay, big size material to nanoparticle size material. Okay, so you are just cutting it into the small. Okay, you are grinding, you are hammering, and you are making that big material into the small. Okay, and in the bottom up, already atoms and molecules are there, and you are using some techniques to prepare the nanomaterial. Okay, so here the nucleation and growth process is there. So what is nucleation, what is growth, and how the nanomaterials are prepared by bottom up approach, that we will see in the next chapter. So in this chapter, what is our approach? What we are looking for the top down approach. Okay, so all the techniques which we are trying to understand in this chapter, what is our approach is top down approach. So let us start with this first technique, which is called as a lithography. Okay, so in our syllabus there are two types of lithography techniques is there. Okay, one is the photolithography and second one is the electron beam lithography. That is given in our syllabus. So before that, we have to understand what is lithography. Okay, what are different techniques for lithography? Can we make lithography in our lab? So if you want to do the lithography, what is the process? Which steps we have to follow? That what we are going to see now. So nanolithography. Okay, so lithography is a broad word. Okay, like materials. Okay, and then we'll see what is called as a nanomaterial. Okay, so like the broad thing technique is a lithography technique, and when we do that lithography at nanoscale, then we call this as a nanolithography. So nanolithography. Nanolithography is one of the most established techniques for making nanostructured materials and patterns. So if you want to make nanostructured materials, and particularly you want some pattern, okay, then in that case you have to use this nanolithography technique, okay, because this technique can give you patterning of nanostructured materials. Pattern nanostructured materials. Nanolithography derives its name from the Greek word nanos, means dropped or small. Okay, you know what is the meaning of nano. Litho means rock, and grapho means to write. Okay, which literally means small writing on rocks. Small scale writing, nanoscale writing on the rocks. So that is called as a nanolithography. Only lithography means writing on rocks. Only lithography means writing on the rocks. Okay? You will understand why we call this as a writing on the rocks. Okay? So this technique is based on deposition. Okay? We have to use some kind of a deposition of some polymer material. Okay? Then we have to etch it. Etching process is there. Etch means we can remove it. Okay? We can take it out that material. Okay? The material you can take it out from the that particular place is called as etching. And writing on a surface, okay, or you can also directly write on the surface. Features with dimension on the order of nanometers. Okay? So if we are able to deposit each and write at the nanoscale, then we call this as a nanolithography. So the lithography process which write the design directly on the wafer is called as direct writing. Okay? Like you have a pen, pencil, chalk, okay, and with the help of that you are directly making design on the paper, on the board. Okay? So if you are doing such kind of thing at the nanoscale, okay, then we call that nanolithography technique as a direct writing technique. Okay, so basically depending upon the type of writing, the type of making pattern at the nanoscale, we have two types. One is the direct writing, and of course second one is the indirect writing. So what is indirect writing? The lithography process which need mask, okay, to write the design on the wafer is called as a indirect writing. So here if you want to make a pattern, okay, you will require a mask. Okay, you need a mask. With the help of mask you are able to make the pattern at the nanoscale. Okay, so that nanolithography technique is called as a indirect writing technique. Okay, indirect writing, we are not directly writing on the surface of the material. We are not able to make the pattern directly on the material. Okay, we need to use a mask, then we have to call this as a indirect writing. So I will give you example, okay, that what are the direct writing nanolithography technique, what is the indirect writing lithography technique. Okay, so before that let us try to understand what is the structure for lithography process. So as you can see, there is a wafer in the top image. Okay, see that the lowest big block represents a wafer. So there is a wafer. Okay, wafer of semiconducting material or some kind of a substrate is a wafer. Okay, on the top of the wafer there is a one more yellow colored material is there. It is called as a photoresist. It is called as a photoresist. Okay, now what is photoresist? Okay, what are different types of photoresist, that we will see in the next slide. So basically you have a wafer. On that wafer, if you want to make the pattern, okay, then you have to use a photoresist. Okay, so you have deposited a layer of photoresist material. Then you need a mask. Okay, so this is a indirect writing method for the lithography. So you have a mask, you are using that mask on the photoresist, and the light is illuminated from the top. Okay, so light is illuminated from the top. Now wherever there is a mask, okay, wherever there is a mask, the light is blocked, right? And where there is no mask, okay, the light can pass, okay, and get incident on the photoresist. So some part of the photoresist get illuminated with light, and some part of the photoresist there is no light. Okay, there is a no light. Okay, so you can use a particular pattern, okay, so that on some part of the uh, on some part of the photoresist the light get illuminated, on the another part the light will not be illuminated, it get blocked with the mask. Okay, so this is the important things what you need for the lithography process. Once you do this process, then can we make some devices? Yes. Okay, we have to see how important this technique is. So suppose you want to make a PN junction transistor, NPN transistor, then you can see how we can use this lithography technique to make the electrodes. Now for example, now you see the below image, you can see this is a transistor, okay, and already there is a N type material is there, P type material is there, and again N type material is there. So this is a NPN transistor. Now in this case you can see this is an emitter, base and collector, and you want to make electrode in that particular region. Okay, in that particular region you want to make the electrodes. Okay, so for the electrode what you have to do, you have to deposit some gold or silver to make the contacts, to make the ohmic contacts. Okay, so in that particular region only you want a material like gold, and in the remaining region you don't want gold. So you want in some region, particularly you can see for emitter there is a block, okay, contact is represented with the brown colored small block. Okay, so that in that region only you want that material like a gold. Okay, in the remaining region you don't want gold. Okay, so if you want such kind of patterning of electrodes, then you have to use this lithography technique. Okay, so these are the very important application of lithography technique, because you all are familiar that the size of the devices, electronic devices, is becoming smaller and smaller. So the size of transistor is becoming smaller and smaller. Okay, and in the transistor you want to take out the contacts for gold. Okay, for emitter, base, collector. Okay, so in that, at that level you have to also take out the contacts. Okay, and for that particular application you have to use this lithography technique, nanolithography technique. Okay. So there are different types of lithography techniques. Okay, there are different types of lithography techniques. Broadly, we are going to see four types of lithography techniques. The first is a photolithography. First one is a photolithography. So in the second one is a electron beam lithography. Okay. Third one is a X-ray lithography, and fourth one is a I-beam lithography. I-beam lithography means ionic beam of ions, ionic beam lithography. So you can see photolithography. So basically there is a substrate, then you need a resist, particularly we call this as a photoresist, and then there is a mask. Okay, there is a mask, and then visible photons are illuminated to make the pattern. Visible photons means our normal light. Okay, normal light is used for the making the patterns for the lithography. So we call this as a photolithography. Photons are used to make the patterns, so we call this as a photolithography. Okay. Second one is E-beam lithography. Now here please note that there is a substrate, okay, then there is a resist, photoresist material, okay, but there is no mask. Mask is not required for E-beam lithography. Mask is not required for E-beam lithography. Okay, so why we call this is a E-beam lithography? E represents electron. So there is a beam of electron is used to make the pattern. Beam of electron is used to make the pattern. Okay, so we are going to see this photolithography and E-beam lithography technique in detail. Okay. The next one is a X-ray lithography. Now X-ray lithography, you can see there is a substrate, there is a resist, photoresist is there. Okay, but again you need a mask because X-ray is illuminated, okay, to make the pattern. Okay, so what is difference between photolithography and X-ray lithography? In photolithography, visible light, photons, are used to make the pattern. In X-ray lithography, X-ray is used to make the pattern. Okay. So as you can see, because the wavelength of X-ray is very small, okay, you can use the pattern as small as 200 nanometer. 200 nanometer or less than that. Okay. So you are able to make the pattern below 200 nanometer. Okay. So for that you need to make the X-rays. But in photolithography, because the wavelength of visible photon lies in the range of 400 to 700 nanometer, okay, what is the limitation is you can make the pattern as small as 500 nanometer. Okay, as small as 500 nanometer. So in that scale, if you want to make the pattern, okay, then you can use visible photons. If you want patterning at a very small scale, then you have to use the X-rays. Okay. I-beam lithography is similar to electron beam lithography. Ion beam lithography is similar to electron beam lithography. Okay, where you don't need any mask to make the pattern. Okay, so there is a substrate, and photoresist is there, and directly instead of electrons, uh, you are using ions, okay, beam of ions to make the pattern on the photoresist. Okay, so once we see the details how photolithography can be done and electron beam lithography can be done, then only the difference in the X-ray lithography and I-beam lithography is only what, instead of visible photons we are using X-rays, and instead of electron beam we are using ionic beam. Okay, so now, as we already discussed, that there are um, two types of writing. One is a direct writing, and second one is a indirect writing. Can you distinguish these techniques, whether it is a direct or indirect writing? Yes, you can easily do it now. So photolithography is a indirect writing because we are using mask. Okay, we are using mask for photolithography, so it is a indirect writing. And for similarly for X-ray lithography, it is a indirect writing because we are using mask. And for E-beam lithography and I-beam lithography, there is a direct writing method. So what are the direct writing methods for nanolithography? E-beam lithography and I-beam lithography. And what are the indirect methods of writing? These are the photolithography and X-ray lithography. Now let us try to understand this photolithography. Okay, so optical or photolithography. Okay, it is both is same. More simple word to understand is a photolithography. Okay, it is also called as a optical lithography because we are using photons, so we also call this as a optical lithography. Okay, so a very important material without which we are not able to do the lithography is photoresist. So you can see in our all these techniques, photolithography, or whether it is a electron beam lithography, I-beam lithography, X-ray lithography, in all types of lithography, the photoresist is required. Without photoresist, we are not able to do the patterning. So what is a photoresist, and what are different types of photoresist? Okay, so there are two types of photoresist. Okay, so basically photoresist is a kind of a polymer or material which is either responding to photons or it is not responding to photons. Okay, so photoresist is a kind of a polymer material. Okay, it's kind of a polymer material which is required for the lithography process. So there are two types of photoresist. One is a positive and second one is a negative. Okay. A positive photoresist is type of photoresist in which the portion of the photoresist that is exposed to light becomes soluble to photoresist developer. Okay, so you can see the image on the right hand side. I have shown two different types of mask. One mask is present at the center, okay, and other mask is there which are at the end of the two glasses, and the middle part of the glass there is no mask. Okay, so if you want to make a pattern, so you can see in the just below the mask there is a silicon is there. Okay, on the top of silicon SiO2 is present. Okay, silicon is there, on the top of silicon SiO2 is present, and on SiO2 there is a photoresist. Now this dark blue, navy blue color represents positive photoresist. Okay, what it represents? Positive photoresist. Okay, and the green color is represented with negative photoresist. Okay, now what we have seen is positive photoresist. is basically once get exposed to light, it get soluble in the developer. Okay, so for positive photoresist, when the light get incident on the positive photoresist, it get dissolved. Okay, so you can see after lithography, only central part of photoresist, positive photoresist, is remained on the SiO2. Why? Because there is a mask. Light is not reaching. Light is blocked for that region. Okay, so when the light is blocked for that region, okay, it is not going to dissolve in the developer, and in the remaining area the light get exposed to the positive photoresist. So the region on which the light is incident, okay, that in that region the positive photoresist has been etched with the developer. It is because it becomes soluble. Okay, it becomes soluble in the developer, so you are able to remove that part of photoresist, right? And once you have got this kind of pattern of photoresist material, then you can deposit the another material and you can remove that photoresist, so you are getting the pattern for that material. Okay, so this is a positive photoresist. Example for positive photoresist is PMMA, polymethyl methyl acrylate. Okay, PMMA. Okay, so this is a positive photoresist. What is a negative photoresist? Negative photoresist is a type of photoresist in which the portion of the photoresist that is exposed to light become insoluble. Okay, so on this photoresist, on this material, okay, if the light is get incident on the photoresist, then it will not get dissolved. It will not get dissolved. Okay, so the example for negative photoresist is Kodak thin film resist. Okay, KTFR. This is a Kodak thin film resist. Okay. So you can see, if you want same pattern on the SiO2, you have to change the mask now, because we are using, okay, negative photoresist. In the green color you can see there is a negative photoresist, and if you want the similar pattern, okay, like on the left hand side, then you have to change the mask. Okay, you have to change the mask. So you can see in the negative the negative photoresist represented with this green block. So you can see the light get incident in the middle part only, and the light is blocked with the mask on each side. So when you put this negative photoresist in the developer, because the light has incident in the middle, that part will not get dissolved in the developer. Okay, and the remaining part, it is not exposed to light, it will get dissolved in the developer. Okay, so you have to use the correct mask based on the type of photoresist. Okay, same mask cannot be used for positive photoresist and negative photoresist. If you use same mask, then you are getting different patterns. Okay, if you use same mask for positive photoresist and negative photoresist, then what you are getting different patterns on the material. If you want same pattern, then you have to change the mask. You have to use different mask for the positive and negative photoresist. Okay, so this is very important, okay, that you have to choose a proper mask for positive photoresist and negative photoresist depending upon your pattern. Now these are the photolithography steps of surface patterning. Okay, okay, so what are the steps which are involved to make the patterning using photolithography technique? Okay, so as I said, okay, uh, photoresist is used for the make the pattern. Okay, so you can see all the lithography techniques are multi-step process. 3-4 steps, 4-5 steps are involved to make the lithography, so it is a multi-step process. As an example, we describe the steps followed in the specific case of photolithography of SiO2 substrate. So as a standard, simple to understand, just for as a representative, we are taking SiO2 as a substrate and we are trying to make the pattern of SiO2 on silicon. Okay, a first step, okay, is to coat the surface of the desired surface with the thin polymer layer of positive or negative photoresist. It is represented in figure A. So you can see the figure A, the lowest block is silicon. Okay, on silicon there is a layer of SiO2. Okay, and on that SiO2 we have deposited a resist. Okay, it will be positive photoresist or negative photoresist. Okay, so a photoresist is nothing but a thin polymer layer, so that is deposited on this SiO2. Okay, that is shown in figure A, which is then covered by a pre-designed, okay, light blocking mask and exposed to UV light. Okay, so some light source is used because it is a photolithography. You can use UV light, visible light or X-rays. Okay, so which type of light you are using, depending upon that it has different types. So in the second step, so first step is what? Deposit a thin polymer layer of photoresist on the SiO2. What is second? Put mask and illuminate the light. Put mask and illuminate the light. Now as I said, you have to choose the mask depending upon the whether you are using a positive photoresist or negative photoresist. If you use negative photoresist, okay, so what happens in negative photoresist? What happens? The area on which the light is incident, it get dissolved. Okay, in the positive photoresist, the area on which the light get incident will not be dissolved. Okay, and after etching in the D, you can see if you use same mask, in one case, okay, in negative photoresist, only that part of SiO2 is removed on this silicon. In the remaining part there is a SiO2. Okay, and if you use positive photoresist, okay, so only that part where photoresist is present, SiO2 is there, and in the remaining region SiO2 is etched. Okay, so by making the pattern of photoresist material, the remaining part of SiO2 you can etch it out. Okay, and in this way you are able to make the patterning of SiO2 on silicon. Okay, on silicon you can make the pattern of SiO2. This is the steps. Okay, so after exposure the cured photoresist remain on the surface as protective coating and the uncured portion are removed by the developer. So figure C, you use developer and remove some part of photoresist. Okay, so in some region there is a photoresist present, in some region photoresist is not present. Okay, and it depends on which photoresist you are using and after exposure of light and pattern, sorry, mask, uh, pattern of mask. So it depends upon type of photoresist, pattern of mask. Okay. So in figure D, as you see, this step is then followed by the etching of the substrate and the final removing of the photoresist. So you can etch the substrate and remove the photoresist. This the type of resist chosen allows having a direct duplication of the mask used as the case of positive photoresist. So if you want exact pattern like a mask, okay, then you have to use positive photoresist, and inverse of it if you use negative photoresist, exactly like in case of film photolithography development. Okay, so this is the steps which are involved in the photolithography. So if you want to make photolithography, you have to follow these steps, and then you are getting pattern of SiO2 on silicon. So photolithography has several limitations. Okay, it is not applicable for curved surfaces. What is the limitations? If the surface is curved, okay, if it is not exactly flat, then we are not able to use photolithography. It is diffraction limited. Okay, no sharp edges. If the edges are very sharp, then there is a diffraction of light effect is there, and because of that you are not getting the exactly sharp edge pattern. You will not get it. Okay, some gradient of material will be there. Okay, photosensitive polymers are must. Okay, the polymers which we are using here, they should be photosensitive. The mask is expensive. If you want to prepare the mask, okay, at the nanoscale, okay, or different types of patterning, then it is expensive. Processing conditions are very harsh, so it cannot be used in biological sample, because in photolithography technique we are using X-rays, we are using UV. Okay, so that is not good for these biological samples. Okay, so photolithography is not correct way for biological samples. Okay, so we will stop here and we will see the next lithography technique in the next next lecture. Thank you.